Assalamu alaikum. This is Iman Wakas, and our topic for today is Introduction to Computing. We'll be discussing the different parts of a computer. There are three main parts of a computer: the input output devices, memory, and CPU. And we'll be discussing how these parts are connected to each other, how the memory is connected to the CPU, and how the input output devices are connected to the CPU, and how the CPU operates all these together. The input output devices, there are a few examples of input devices. There is keyboard, mouse, sensor, microphone, scanner. All of these are input devices. For output devices, we have our monitor screen is an output device. The speakers in our computer are an output device. Printer, hands of a robot, all of these are output devices. Now, memory is anything that can store, retain, and recall information. Examples of memory could be a hard disk, it could be a solid state drive, a floppy disk, a piece of paper, etc. All of these are forms of memory. It is a storage device, it can store, it can retain, and recall information. There are three main characteristics of memory: capacity. Capacity is the number of bits or bytes that a memory can store. For example, 128 kilobits or 128 kilobytes, 256 megabits. This is the storage, the quantity of data that a memory can store. And organization, how the locations are organized inside the memory. For example, if we say that we have a 128x4 memory, that means we have 128 locations inside the memory, each storing 4 bits. Access time is how long it takes to get data from the memory. Now, the memory is consists of semiconductors as well as non-semiconductors. Like on the bottom left, we have a floppy disk. For there are two major types of memories, ROM and RAM. ROM is read-only memory. In other words, it's also known as permanent memory. And RAM is random access memory, which is also known as temporary or volatile memory. So first, we'll be discussing read-only memory (ROM). The first type of ROM is mask ROM, which is programmed by the IC manufacturer when it is being manufactured, and it cannot be reprogrammed. It is only programmed by the manufacturer. Then we have programmable ROM, PROM, which is one time programmable ROM, which means you can only program it once, and after that you cannot reprogram it, you cannot erase it, you cannot change it. Then we have erasable programmable ROM, EPROM, which basically the contents inside the ROM can be erased using ultraviolet radiation, and that process takes up to 20 minutes, and all the contents of the ROM are erased together. Then we have EEPROM, which is electrically erasable programmable memory, which uses basically it erases the contents of the ROM electrically, and all of the ROM it is erased instantly. Each byte can be erased separately. So this is an advantage of EEPROM. Like the bytes, if you want to retain few of the bytes and you want to keep them, and you want to delete only a few, then you can keep them and you can delete the ones that you don't want. But the disadvantage for EPROM was that it completely all the contents of the ROM were erased. You cannot erase only few of them. In flash ROM, it is erased in a flash. The entire device is erased at once. Then we move on to RAM. Static RAM is made up of transistors. Its advantages are that it's faster and it does not require refreshing, but it's also expensive, and it has high power consumption. Dynamic RAM, on the other hand, is made up of capacitors, and it is cheaper compared to static RAM, and it has high capacity and less power consumption. However, it's also slower and it requires refreshing. Then we have the third type of RAM, which is non volatile RAM. It is made up of static RAM, battery, and control circuitry. Its advantages are that it's very fast, it is non volatile. However, its disadvantage is that it's really expensive. Moving on to CPU. Now, the CPU, what it does is that it should execute instructions. It recalls the instructions from memory step by step and then it executes them. This is the memory pin, which is connected to the CPU. There is where we have the data bus, which is which is connected with D0 to D7, and we have the address bus, which is connected to A0 to A, like address 0 to address n minus 1. Then we also have the write enable pin. We also have the chip select pin, and we also have the VCC and the ground pins that are connected. This is the memory connected with the CPU. This is how it's connected. Then the two operations can be performed with the memory and the CPU, writing operation and the reading operation. These are the graphs explaining how the writing operation works with respect to time. So the major difference basically between writing and reading operation is that the chip select has to be zero. First of all, in both operations, the chip select is zero. While writing as well as while reading, the chip select is zero. There are addresses going on, and there is some data that we need to write. While writing the write enable, it should be noted that the write enable should be zero while we're performing the writing function. So while we're writing some data into the memory, our write enable pin should be zero. However, in a reading operation, as we can see clearly that the write enable pin should be 1. It should not be 0. The write enable pin for reading operation should be 1. Likewise, over here, chip select should be 0, and data, there should be some particular data that has to be read. But the only main difference, is that in reading, our write enable is 1. However, in writing, our write enable is 0. Now, how the input output devices are connected to the CPU. The CPU has a lot of pins which connects the respective input output devices. And this is how buses are used to connect the CPU with all the input output devices uh, attached with the computer. And this is the memory. Memory also has all these buses which connects the input output devices and the CPU. So this is how all three of the main parts of the computer are interconnected with each other. The CPU is the main head, and the buses are basically inside the CPU. And these buses connect the input output devices to the memory. And how do we manage to connect the input output devices in memory to CPU? There is a logic circuit inside our computer. That logic circuit enables our chip select when address is between 0 and 15. As we can see in our case, our addresses inside the memory are starting from 0, ending at 15. So when our address will be between 0 to 15, this logic circuit will enable our chip select, and then our chip select will select the particular address the particular location which it has to go to. Now, how can we make this logic circuit? First of all, the first step that we do is that we write our address range in binary. Here, in our case, our address range is 0 to 15. So basically, what we do is that we write 0 and 15 in binary. Using 8 bits, we write 0 and 15 in binary. Then what we do, we select the similar part of these ranges, and we can see over here that the same part we separate the fixed part of the address, right? So we can see over here that only the four zeros at the left, they are similar in both cases. So we select them, we separate them, and we use NAND gates to design the logic circuit whose output will activate when this fixed address is given to them. So this is the NAND gate and the NAND logic circuit we've made using this fixed address. All our inputs are 0, and then when all our inputs are going to be 0, our chip select will be enabled. Moving on, here is another example for the address decoder for addresses of 300 to 3FF. Again, we repeat those steps 1, 2, 3. We write the address range in binary 300, where 3 is 0011 and 0 zeros are 0000. Then we write 3FF in binary. We separate the fixed part of the address. We can clearly see that the fixed part of the address is 3, right? So 00011 is the fixed part of the address. So we separate it and we design the logic circuit using this fixed part. As we can see, 0 is in places A10 and A11. So we've made a NAND gate in a way that A10 and A11 are giving 0 inputs and A8 and A9 are giving 1 input. When this combination will be met, our chip select will be enabled. Moving on, this is what we find inside a CPU. There is a program counter, there is an instruction decoder, there's an arithmetic logic unit where all the operations are performed: addition, subtraction, multiplication, division. All of this is performed inside the ALU. And then we have the registers inside a CPU which store information temporarily. Now, how the computer works, this is there a computer always works step by step in a series of instructions. It follows a series of instructions. Here in this case, we have our instructions in this blue, on the top right, in this blue text box. We have our instructions, and we have our memory from 0 to 7. So one by one, we'll be following these instructions and we'll see how the computer operates. At first, our program counter, as we can see inside the CPU, our program counter is 0. That means we'll be reading the address 0. This 0 goes to our address bus. And our read function, the control bus, basically gives the instruction of reading this address. As we can see here, the data from the address 0 is sent to the instruction decoder. The data was 31 was stored inside the um, location 0. So that data is inside the instruction decoder now. It has moved inside the instruction decoder. Next step is we move on to 1. The program counter increments itself. Our first instruction, first of all, was A. The data in 17, input output 17, should be moved in register A. So our address bus is now showing 17. So we'll see what our input output 17 gives us. The data that it will give us, it will move inside the register A. So we will read what data is inside the input output device 17. Data is 9, as we can see over here. So this 9 will basically move inside the register A. According to our first line of instruction, the data from the 17 input output device has to move inside the register A. And this is what has happened. Now, since our PC was incremented to 1, now we'll be reading the next statement. Our location at 1 is our data at location 1 is C4. We'll be reading that C4. As you can see, it's come inside the instruction decoder box. So the next instruction for us is A. What the contents of register A should be transferred to the contents in the register B. So the contents currently in our register A, we can see there is 9 stored inside our register A. So 9 will basically move to B. We have executed our second line of instruction. Now moving on to, now the PC is again incremented to 2 and it went inside the address bus. The location 2 stores the data 26. Now this 26 will be read and it will go inside the instruction decoder. So our next instruction is the data or the contents of 6 address should basically move to A. Right? So our address bus gives us 6 and the contents of 6, which was 5, goes into the data bus and they go inside A. So we've executed our third line of instruction. Now our program counter increments to 3, and the 3 is passed on to the address bus. Now we will be reading our data inside 3, which is 81. 81 goes inside our instruction decoder. Our third instruction is that A plus B should be stored in A. So the sum of A and B should be stored in A. So here we are executing this line of instruction. Sum of A and B, which is 5 and 9, should be stored in A. 5 plus 9 is 14, which is hexa for E. That E is stored inside register A. Then the program counter increments again. 4 is stored inside our address bus. We read the fourth instruction, which is EA, and that is stored inside the instruction decoder. Our fourth instruction is that the contents of A, register A, should be stored inside the location 7. So whatever is stored in our register A, its contents should be stored inside the location 7. So E is currently stored in our location A. So that E will basically move inside our location 7. It will be written. So here now, this is the first time our write function is being implemented and it's being written. E is being written inside the location 7. So we have finally executed all these instructions, and this is how the computer works, how the address bus, data bus, and control bus works, and how the registers inside a CPU work. This is another example how the instruction decoder works. We are given the instruction consists of opcodes, three digits for opcodes, and uh, 1, 2, 3, 4, 5 digits for operand. Opcode has different meanings. If we write 000 in opcode, that means that the x, whatever x is, should be transferred to register A. If we write 001, that means whatever the contents of location x inside the memory are, those contents should be transferred in A. Then 010 means these are all these examples of what opcodes mean. And this is basically how the instruction is written, how instructions are written. Now we have two types. We have microprocessors, general purpose microprocessors, and we have microcontrollers. The main difference between the two is that microprocessors, they do not have RAM, they do not have ROM, they do not have input output ports. They basically have input output ports on the chip itself, but they have no ROM or RAM installed inside them. Right? For example, Pentium examples of microprocessors are Pentium, Intel, PowerPC, or Spark, and applications are inside the desktop, inside the laptop, inside the servers, PCs. Microprocessors are inside the servers and PCs, but there is no RAM or ROM inside the microprocessor. However, a microcontroller has microprocessor in it, has RAM in it, has ROM in it. It has timers, it has input output ports on a single chip. This is the main difference between microprocessor and microcontroller. Microprocessor does not come with the RAM and ROM, but microcontroller comes with its own RAM and ROM. And examples of microcontrollers are 8051 Intel and AVR Atmel and ARM Advanced RISC machine. All of these are examples of microcontrollers. Application is a TV remote control or video games or robots. These are microcontrollers. Here's a diagram that explains the difference between microprocessors and microcontrollers. The blue one on the top left is a general purpose microprocessor, and it is attached with with a separate RAM, ROM, timer, and IO port, etc. But a microcontroller consists of all these things inside. Right. Moving on to embedded systems. An embedded system is controlled by its own internal microprocessor or microcontroller, right? Like an embedded system has its own microprocessor and microcontroller, which is as opposed to an external controller. That we do not Embedded systems do not have an external controller; they have their own microcontroller. And a PC is connected to various embedded products. A keyboard is an embedded system, a printer is an embedded system, the AC in our houses, the inverters that we use, the printers that we use, the disk controller, sound cards, mouse, all these devices, the mobile phone that we use, all of these devices are embedded products, and they are embedded systems. A printer gets data and prints it. A mouse takes coordinates and sends to the PC. All these are examples of embedded systems because they have their own internal microprocessor. Here, there are a few examples in computing. Embedded products could be laptop, could be PC, could be laser printer, could be copier, scanner, digital camera. In cars, there are anti-lock brakes, engine control, climate control, navigation, trip computer. All of these are examples of embedded products. Choosing a microcontroller for your embedded system. So these are all the factors upon which we decide our microcontroller. Firstly, its speed. We have to see if we need a high speed microcontroller or a slow speed microcontroller would work for us. We have to see its speed. We have to check its packaging. Is it dual inline packaging or is it quad flat packaging? That depends on whatever we're making. That depends on the application for which it has to be used. Then we have power consumption. It is critical for the battery powered products. We have to see how much power we can supply. So according to that, we'll choose a microcontroller. Then the amount of RAM and ROM on chip, the number of timers and input output pins on the chip, the costs, and the availability of the compiler, simulator, debug. All of these are factors that basically decide our microcontroller. The AVR microcontroller family, two basic architectures. There are two basic architectures in the AVR, which are the two basic architectures is the Harvard architecture and the von Neumann architecture. We'll be studying them later on. The AVR stands for Advanced Virtual RISC or ALF and Vigard RISC. AVR is an 8-bit RISC single chip microcontroller with Harvard architecture. The difference between CISC and RISC is that CISC is a complex instruction set computer. It has a large number of instructions, and those instructions perform specialized tasks, and they're used infrequently. And it has a large variety of addressing modes, typically from 5 to 20 different modes. It has a variable length instruction format. This was you normally used in older times. It's not used a lot in modern days. RISC, however, is used in modern days because it is easier to use. It has relatively few instructions, it has few addressing modes, and it has a fixed length, easily decoded instruction format. That is why it is used instead of CISC. So, as I said before, there are two types of architectures, von Neumann architecture and Harvard architecture. The difference between the two is that the von Neumann architecture has the same bus which is used for accessing both the code and the data. And architecture, however, on the other hand, has separate buses which are used for accessing code and data memory. That means we need four sets of buses: a set of data bus for carrying data into and out of the CPU, a set of address bus for accessing that data, a set of data buses for carrying code into the. This is basically an example of Harvard and von Neumann architecture. We can clearly see in Harvard architecture there are four different sets of buses. There are CPU and there are different buses for data memory and code memory. So to access code memory and data memory, we need separate buses. However, in the von Neumann architecture, we can access together. We can access the code memory and the data memory together in a single bus. So this is the main difference between the two. This is the simplified view of an AVR microcontroller family. We have CPU, we have ports, input output pins, we have RAM and ROM, and timers. This is a block diagram, and basically, this is how we decode the numbers, AVR part numbers. AT means atmel, X mega is the group, or mega is the group, or Tiny is the group, and the last four digits are basically the memory. It gives us the memory. Flash is 64K over here. Flash is 128 kilo over here. Flash is 44K over 4K over here, and 256K over in the last one. So this is all for today. This was our introduction to computing. I hope you understood whatever I